This is the solution video for the box problem from the optimization extension activity. Okay, so we're making a box from a piece of tin, okay, that measures 20 centimeters by 20 centimeters. So let's add that to the diagram. I know that this is 20 all the way across. This is 20 all the way down. Okay, and I'm going to add back in, right, there's a line here. Okay, because I was talking about they're cutting a square corner out of this end and a rectangle out of this end, so I'll be able to fold up the box as shown here. Okay, so let's start identifying some things that we don't know. Okay, I don't know what that length is of the square, so we'll call that x and x. Okay, now that I split this up a bit, okay, this square down here, this square here has to match with that, right? Because the front and the back have the same dimensions. So this is also x right here. Okay, and over here, okay, lots of x's on here. Okay, I don't know for sure what this distance is down here. Okay, so we'll call that y. Y. Okay, this dimension on the lid has to match this dimension on the bottom. So that's also y right there. Okay, and last but not least, this piece in here, because we're going to need it, okay, because I know both of these, they're both x, then this leftover piece is going to be 20 subtract the 2x. Okay, if I knew x was 1, I'd know this would be 18, 20 minus 2. So what do we know here? Well, we know the area or the dimensions of this. Oh, okay, yeah, this is 20 centimeters. So one relationship between x and y, if I use this side right here, okay, I have 2x plus 2y would be equal to 20. Okay, if I divide everything by 2, that means x plus y has to equal 10, which I suppose makes sense. Okay, this split has to be half the length of the box. Okay, so let's say we'll rearrange that to y equals 10 minus x, because we're probably going to need to do that in an optimization problem. Okay, our goal is to find the largest volume of box, so the biggest box I can make from this setup. So that means I need to know what my dimensions are, so I can fill in volume equals length times width times height. Okay, well, the length of the box, okay, is probably going to be this piece right here. So that would be 20 minus 2x. Okay, the width of the box would be this part, which is y. Okay, and the height of the box, okay, when I fold it up, is going to be one of these right here or this. Okay, and that's x. Okay, now I can substitute, okay, my y. So I have 20 minus 2x, 10 minus x, x. Okay, so there's my volume. Okay, and now I can start working towards the derivative because I'm all in terms of x. Okay, before I do that, I'm going to tidy this up a bit. I'm not going to completely expand it out or anything, although it wouldn't be too bad to do that, I guess. I'm going to do some rearranging here because I noticed this 20 minus 2x, we did this earlier or something like it. I can factor out a 2 here. So 2. I shouldn't say that. We didn't do something exactly like it. But if I go back up here, right, I notice these are all divisible by 2. And this is kind of related to it. So 2 times 10 minus x times 10 minus x times x. So grouping some things together, that means I have 2x times 10 minus x squared. Okay, the reason I did all that, again, you could just expand this all out, okay, and see what you get. This is a pretty nice product rule for taking my derivative. So v prime equals, okay, derivative of the first part, which is 2 times the second part, okay, plus the first part, 2x, times the derivative of the second part. That's going to be a chain rule. So I bring down my 2, multiply it by 10 minus x, okay, and then that's power 1, and then take the derivative of the inside of the brackets, which is going to be negative 1. Okay, so there's actually some factoring I can do here. Each of these has a 10 minus x, so I can factor that out. Okay, and there's also a factor of 2 sitting in both of these, so let's factor both of those out. So 2, 10 minus x. Okay, leaving behind from the first term, or first group, so I'm talking about this right now. Okay, all I'd have left over is 10 minus x. Okay, from the second group of terms, right, I've removed a 2 and the 10 minus x. So I'm going to get left with, and I see that negative 1 there, so I'm going to get left with minus 2x. Whoops. Minus 2x. Okay, so 2, 10 minus x, and tidying up what I have left there, that is 10 minus 3x. Okay, so the advantage of leaving it in product rule form is now my derivative is already factored. Okay, I have it in a completely factored form. So when I set this equal to 0, okay, it's going to be pretty quick to identify my critical points. Okay, either it's coming from this factor, so that's x equals 10, okay, or it's coming from this factor. Okay, I know it's a little backwards to what we normally do, so let's just write it out quick. That's 10 minus 3x would have to equal 0, so 10 would have to equal 3x, so 10 thirds equals x. Okay, well, sorry, that's not 0, that's 10. Okay, x can't be 10. Okay, and the reason why, if x was 10, that means this square would go all the way to here, and it would basically consume the entire box, right? If those squares were all 10 by 10, I'm just going to draw an overlay here for a second, right? There'd be, right, there's a 10 by 10 square, another 10 by 10 square, and another one, and another one, and that would just eat up all the tin. Okay, so that doesn't work. Okay, so it's got to be 10 thirds. So now let's figure out what our other dimensions would be. Okay, x was the height. Okay, y was the width, and y was equal to 10 minus x, so 10 minus 10 thirds, which becomes 20 thirds. Okay, so that is the width. Okay. And the length of the box, okay, the length was 20 minus 2x. Okay, and if I run that through, we get 40 over 3 is the length. Okay, so those are the dimensions that give us the biggest possible volume. Okay, although we should quickly check. So again, I'm going to grab my derivative here. We should quickly check and see if that's actually a maximum, because that's what we're going for here. So that means I need to take my next derivative. Okay, if this was my v prime, I am now going to quickly check v double prime. So 2, that's a constant, so I can ignore that for the moment. And I have another product rule. So derivative of the first is negative 1 times the second, 10 minus 3x. Okay, plus the first, 10 minus x, times the derivative of the second, which is negative 3. So this equals 2 times negative 20 plus 3x minus 30 plus 3x. So I've got 2 times negative 50 plus 6x. Okay, and I was checking x at 10/3. So v double prime of 10/3 is equal to 2 times negative 50 plus, let's see, 6 times 10/3. A third of 6 is 2, so 20. This whole thing becomes negative 60. Okay, so my second derivative is negative. That means the function is concave down in that interval. And yes, this is a max in that region. Okay, so again, there's my dimensions. The height is 10/3, the width is 20/3, and the length is 40/3, which for decimal approximation, right, this is like 3.33, right, 3 1/3. This is 6 2/3, and this is 13 1/3. Okay, thanks for watching.